Okay, how you doing? We're going to talk about something called the rational roots theorem. And this is just a property that holds true for all polynomials. And if you think about it, when I go through it, I'll explain how it relates to things that you've been doing. But what we have here is we have this rational expression of c divided by d. And this is the important thing. That this is really what we're basing it off of, is we're just saying that some rational expression that I'm going to create. So some value that I'm saying is a factor. So I'm saying that this c divided by d is some factor of my polynomial. And based off of that, what I'm saying to you is that they have to be relatively prime. So what does it mean to be relatively prime? So two numbers are relatively prime as if they have nothing in common. I mean, you can't reduce it. So if you make a fraction out of c and d, it can't be reduced. If you make a fraction out of c, some value divided by another value that can be reduced, then they're not relatively prime. For instance, 7 divided by 3, 7 and 3 are relatively prime. 6 and 13, relatively prime. While 6 is not a prime number, 6 and 13, there is nothing that goes into 6 that goes into 13, and vice versa. So they are considered to be relatively prime to each other. Numbers that aren't relatively prime, 2 and 4. 2 and 4 can both be reduced. Okay, if you had a fraction of 2 over 4, it can be reduced. So just thinking about this rational expression is that if you take something, okay, after we go through these problems, that can be reduced, that isn't something that you need to worry about creating. So what we need to look at then is that c, okay, so where do I get this c value from? Well, c is going to be a factor of whatever the constant is that's in my polynomial. And then d is going to be a factor of whatever the leading coefficient is. And for us to be able to apply this theorem, there's some other little small rules that apply, and it can only apply the theorem if the coefficients are integers. So if you have a problem where it's a polynomial that the coefficients are fractions, you are going to have to clear the fractions from the polynomial before you can even begin, okay, to apply the rational theorem, just so the rational root theorem. So that's important. So let's talk about an example of how I can apply this rational roots theorem. So I'm going to walk you through a problem to show you how it is that I apply that. And the reason for this is because when we start getting the polynomials that have higher and higher and higher powers or degrees, there is no special laws that start to apply, like say the perfect squares or perfect cubes or sum of cubes and the difference of cubes and the difference of squares. And there is no like set formula for it. So when we start to factor these things, we're really just going to guess and check, but we're going to base it off of certain properties. And one of the certain properties is that if something has a rational root, it's going to apply and hold to all of these things. So let's go ahead and check that out. So let me erase this so I have some room. So I have this problem off to the side that I'm going to write up to the top here. And basically what essentially I'm trying to do for this problem is I'm trying to find all the roots of the problem. And if there are no rational roots in the problem that I write, then there are no rational roots. And therefore I've got to find irrational roots. And you'll learn later on how to do something like that. So I have this polynomial. So p of x is the notation for polynomial. Is equivalent to 3x to the 4th minus 4x cubed plus x squared plus 6x and then minus 2. So here's my polynomial that I have right here. So p of x, 3x minus 4, minus 4x cubed, plus x squared, plus 6x, minus 2. So there's my polynomial. And what I want to do is I want to find the roots, okay? And what you should know about this polynomial right now is that there are going to be 4 roots, because the degree, okay, of the polynomial determines how many linear roots you're going to have. So if this determines how many linear roots you're going to have, so that means that you have some roots that are x minus r equals 0. Okay, so you have 4 of these roots that are in existence, and our goal is really to find out what r is. Now, doing this, okay, you could start guessing and checking with numbers. You start with all your integers, okay, but there could be some rational roots that are fractions. So the way that you have to do this, okay, is we're going to take a look at what c is. And c, okay, applying this rational root theorem, c is going to be the factors of my constant, okay? My constant in this problem is negative 2. So what I'm going to do is write out all the factors of negative 2. So I could have 1 times negative 2, or I could have had negative 1 times 2. So those are all the factors of negative 2. So d, okay, D is positive 3. So what are all the factors of positive 3? So positive 3, I could have had 1 and positive 3, or I could have had negative 1 and negative 3. So the next thing that I now want to do here is create what is C over D. So here we go. Things I need to check. Okay, when I do C divided by D, what I'm going to check for here is that whatever divisions I do, I'm just going to make sure they're relatively prime because I don't want to deal with anything that reduces. Okay, so 1 divided by 1 is 1. So what I'm going to do here is systematically take this number and divide it by all of these. Or you can look at it as take all of these numbers and divide it by each one of these. So let's do it that way actually. Let's take all of these and divide it by 1. So I get 1, I get negative 2, I've got negative 1, and I've got 2. So that was all of these divided by 1. I'm going to do the same exact thing now dividing it by 3. So if I take all these divided by 3, 1 divided by 3 is 1/3. Negative 2 divided by 3 is negative 2/3. Negative 1 divided by 3 is negative 1/3. And 2 divided by 3 is positive 2/3. Okay, so what I've created here is C divided by D. Okay, and that's all of them. So I'm going to keep going. So I have negative 1. But please note that negative 1 is just going to change the sign. So I already have 1 divided by negative 1. I'm not going to write duplicates. So 2 divided by negative 1 is positive 2 and so forth. So you'll notice that the negative 1 I'm not going to have to do. And you'll also note here that this negative 3 here, I'm not going to have to do it because 2 divided by negative 3 is negative 2/3. Okay, so I have all of those things. So basically what I've got here is that I'm not going to take any repeats, and so I'm done. So what this means, okay, this C over D, is that these now are all of the possible rational roots. There are no others, meaning that the number 4 can't be a root to this problem, and it won't be because it has to follow the guidelines that it's a factor of C and D, okay, that rational expression. So these are all the roots that I now have to check, and that's if any of these are actual roots. It doesn't mean that they are a root, okay? It means that out of these possible 1, 2, 3, 4, 5, 6, 7, 8, out of these possible 8 answers here, okay, 4 of them could be rational roots, okay? It could be one of them is a rational root, it could be 2 of them a rational root, 3 of them a rational root, but at most 4 of these 8 could be rational roots. And the others then could be my irrationals or my imaginary numbers. We don't know until we go through and calculate. So from this point, okay, instead of guessing and checking anymore, I've basically dwindled my guessing and checking down to 8 particular problems here for rational roots. And the way that we start guessing and checking is synthetic division. So the first thing that I would do here is I would check that 1, okay, so here's my root. All right, and the thing we don't want to confuse here is with x minus r, okay, when we're saying that that was a root, and we took the opposite of this r, we don't want to take the opposite of these. We're saying that this is the actual value of the root. So when we were doing the x minus r, it would have had an expression like x minus 1 equals 0, and then you would have said x equals 1. So you would have been like, oh, 1 is a root, right? So we don't want to change the sign of these, we just want to do them as they are. So the way we do synthetic division, okay, is you take this number here, okay, and we write out the coefficients, and we just check. So here we go. We have 3. X to the 4th, x cubed, so we have a negative 4. X squared, we have a positive 1. 6x is a positive 6, and negative 2. So now what I'm going to do is my synthetic division. The first step is you always bring the first one down right away. You don't do anything with it. So now I start multiplying and adding. So 1 times 3 is 3. Negative 4 plus 3 is negative 1. 1 and negative 1 is negative 1. 1 and negative 1 is 0. 1 times 0 is 0. 6 and 0 is 6. 1 and 6 is 6. That makes this a remainder of 4. So what that means is that if I have a remainder here, remember, that it's not a root. So 1 doesn't work. So I'm going to cross it out. That didn't work. So I'm just going to go down my list. Okay? So now I'm going to go to negative 2. So negative 2. So 3. Negative 4. 1, 6, negative 2. So I bring the 3 down. Okay, so I'm just going to leave this part here. So 3. So negative 2 and 3. So now I have negative 2 and 3. I've got this is negative 6, makes negative 10. Negative 2 times negative 10 is positive 20, which makes 21. Negative 2 and 21 makes negative 42. So what you can kind of notice here that there's no way I'm going to make a positive 2 out of this. So I know negative 2 doesn't work. So let me get rid of that. So negative 2 doesn't work. So let's check -1. So -1, I bring the 3 down. Okay, that makes -3, which makes -7. That makes +7 when I multiply. And that makes 8, so that makes -8, okay, which that then makes -2. And -1 times -2 is +2. -2 and 2 is 0. So what I've got here is a root of x being of -1. So I found a root that has a -1. And now what I have here is, what I want you to note is, okay, if this was an expression, this here would have been x, this would be x squared, and this would be x cubed. So what I'm going to do, okay, is because I'm trying to find the factors of this one, I'm just going to continue on with my values that I have for this, okay? Except my new values up here are going to be 3, -7, 8, and -2. So I hope you understand what I mean by that. But essentially I'm just sticking these up here and going through the problem again. So I've got -1 as a root, I'm just going to circle it. Okay, so here we go. I'm just going to change these up here really quick. So this is a 3, this is a -7, this is an 8, and this is a -2. Okay, so note that my values were 3 and -2 still, so I still have these values that apply. Okay, so I'm just going to go through now and just check some others. Alright, so here we go. So now I'm just going to check maybe, I don't know, let's check 1/3. Let's take a guess. Let's skip over 2. I doubt 2 will work. -2 didn't work. I doubt 2 is going to work. So let's try 1/3. So 3 comes down. Okay, so I'm going to put 1/3 here. So 1/3 of 3 is 1. And then what I'm left up here is -7 and 1. -7 and 1 just so happens to be -6. Okay, 1/3 of -6 in this case is -2. So 8 and -2 makes 6. Okay, 1/3 of 6 is going to be 2. So 2 and -2 is 0. And now what I have is that 1/3 also happened to work for this particular one. So I've got 1/3 and I've got -1. So there's another root that worked. And lo and behold, what that created here is that if you take a look at this, and if I fill this in for my quotient, is I have 3x squared minus 6x plus 6. So this is now a quadratic, and now I can use problems that I've done before. So here we go. So 3x squared, so I'm going to just factor this and say it equal to 0. So 3x squared, it was minus 6x, it was plus 6. I'm going to say equals 0. I'm just going to factor it. If I take a 3 out, I'm left with x squared. Minus 2x plus 2, so equals 0. So can I make -2 from a +2? And if so, then okay. I don't think I can. So what I'm going to have to do here is I'm actually going to have to use a formula for this one. So I'm going to divide everything by 3. And I'm left with x squared minus 2x plus 2 equals 0. So now I can go through and I can use the quadratic formula, or I can use completing the square. I'm going to choose to use completing the square here, so I'm going to move my +2 over, make it -2 here. Okay, so I'm just going to go through completing the square. And what I have here is take half of that, which is makes -1, square it, so adds 1 to both sides, add 1. And then what I'm going to do here is I'm going to write what I would have, so this is going to be x minus 1. That quantity squared is now going to be equal to -1. Take the square root of both sides. I'm going to put this to work right here. Take the square root of both sides, you're left with x minus 1 is equal to plus or minus I. Okay, the square root of -1 is plus or minus I. So I'm left with x equals 1 plus or minus I. And those are my other roots. And notice that I should have 4. So 1, 2, and then this is actually 2 because of the plus or minus, which makes my 4 roots. So what you have here now is that I had 2 rational roots and I just happen to have 2 imaginary roots. So what this is saying is it doesn't mean that this is going to have 4 rational roots. What it means is that if it has any rational roots, it has to be of these options. So I hope that helps with any work you're doing over the weekend or whatever it is you have homework for, but that is how you apply the rational root theorem.